So, right. Let's have our third talk in this morning session. We have Professor Liu Tao from the Hong Kong University of Science and Technology telling us about Pulsar Polarization Array. So Professor Liu works on a series both phenomenological series and also ultraviolet complete level series to explore physics beyond our current knowledge. So he also want to connect it to experiments. So he divided strategies to explore possible phenomena beyond the standard model. So today he's going to tell us about this pulsar polarization array technique and its application in detecting this kind of ultralight axion-like dark matter candidate. So let's welcome our speaker.
All right. Before I start, let me thank first for this invitation. And today I will give an introduction about the pulsar polarization array. And this concept is probably new to some of us, so I will try to make this talk pedagogical. We know pulsars are one of the four greatest discoveries in 1960s. And from the data collected by Jocelyn Bell in 1967, and we can say they looks too regular to be anything but man-made. But now we know these data are just signals generated by the remnants of stellar evolution. We know somehow the pulsars have important scientific values, and because of this significant discovery, Anthony Heurich, who is supervisor of the Jocelyn Bell, won Nobel Prize in 1974 for his decisive role in the discovery of pulsars. And as for Jocelyn Bell, she was overlooked by the Nobel Prize, but in 2018, she got a special breakthrough prize in fundamental physics. And following this effort, in 1974, House and Taylor discovered the first binary pulsars with the companion being a white dwarf. And then, by performing the observation of the orbital decay for this pulsar binary, they got the indirect evidence for gravitational waves. And this is the first evidence for the existence of gravitational waves. And also because of this achievement, House and Taylor shares the Nobel Prize in Physics in 1993 for the discovery of a new type of pulsars, a discovery that has opened up new possibilities for the study of gravitation. And we know pulsars are excellent astronomical clocks. And because of the misalignment between the spinning and the magnetic axes, the pulsars can send pulses with extremely high regularity. And this is especially true for millisecond pulsars. And the millisecond pulsars are later stage pulsars. And usually they are generated from a binary. And then by absorbing mass and orbital angular momentum from its companion, and the millisecond pulsars usually spin much faster and also more stable compared to normal pulsars. And in this plot, we can see the cluster of millisecond pulsars, And here, the red color denotes that they are from the binary pulsars. Okay, they are binary pulsars. And pulsars are very rich in our galaxy. And so far, about 3,000 to 4,000 pulsars have been observed. And among these pulsars, about 10% to 20% are millisecond pulsars. And with next generation radio telescopes, about 20,000 pulsars are expected to be discovered. And because of these nice features about the pulsars, actually as early as 1980s, actually the late 1970s, okay, to construct a network of widely distributed and well-timed millisecond pulsars as a galactic scale timing interferometer. And just think about it. For the perturbations to the fabric of our space-time, okay, if there exists perturbation to the fabric of the space-time, then some timing residues could be generated for the pulsars within our galaxy in a correlated way, okay? And because of this fact, it has been suggested to use such a pulsar timing array to detect the gravitational waves, especially for the frequency band of nano-Hertz. And then, together with the other gravitational wave detectors, such as ground-based detector like LIGO, and space-based interferometers like LISA, and the CMB polarization measurement, somehow we have a nice coverage for the frequency band of gravitational wave detection, especially for the range below 1 kilohertz. And because of the scientific significance of such a task, in last decades, a series of pulsar timing array programs have been operated or planned. And here is a list of the leading pulsar timing array programs. This one is POX PTA program, and it is led by Australia. And this one is European PTA program, which is led by Europe, and nanograph, it is led by Canada and the US. And this is Chinese PTA, which is led by China. And also, we have the next generation PTA program, SKA PTA. And these two panels shows, okay, these two panels are just some cartoons, okay. The left one shows low frequency antennas in Western Australia, and the right one shows mid frequency dishes in South Africa. And so far, over 80 millisecond pulsars have been monitored by the global PTA network over a time span of years. And the future observation, for example, by a SKA and FAST, can increase this number to several hundreds with a higher timing precision. And here, the core value for pulsar timing array is a cross correlation. That is correlating the correlating the timing data across all arrayed pulsars. And as highlighted in this pioneering paper by Hillians and Downs, when data from several pulsars are cross-correlated, this common signal will allow one to dig into the pulsar noise to detect a possible common gravitational wave signal. And the Hillians and Downs curve, which is known probably to many of us, encodes exactly the correlation of timing residues across arrayed pulsars that would a common gravitational wave signal. And here, this left panel shows exactly this Helians-Dance curve. And the x-axis represents the angular separation between any pair of the pulsars. And as for the y-axis, this is a measure of the correlation strength. Usually, it is the two-point correlation function. Okay, it is a factor of the two-point correlate function. And about 1 year ago, the four leading PTA collaborations reported their progress in the measurement of the Helians-Dance curve. And from these four plots, we can see a consistency between their data and the Helians-Dance curve. And this outcome strongly supports the interpretation of the stochastic gravitational wave background for their data. Certainly, this is a milestone for gravitational wave astronomy, and also a learning success for the PTA programs. But this is not the whole story. And we know pulsars are also excellent astronomical linear polarizers. And usually, the polarization profiles are measured for calibrating the observation of pulsars. And for example, if we go to this database, Australia Telescope National Facilities Pulsar Catalog, then we can say for many pulsars listed in this database, actually the polarization information has been provided. This naturally raises the question, can we cross-correlate the pulsar polarization data as done for the timing data to give a full play to its capability in exploring astrophysics and fundamental physics? And then, motivated by such a consideration, with Louxi Zixiang, who was my undergraduate student and currently a PhD student at Stony Brook, and also my collaborator, Jin Ren, who is a physicist from IHAP, we proposed to develop the Pulsar Polarization Array. And as highlighted in the abstract of this paper, with the same data acquired for pulsar timing arrays, we propose to develop pulsar polarization arrays to explore astrophysics and fundamental physics. And as in the case of pulsar timing arrays, pulsar polarization arrays are best suited to review temporal and spatial correlations at large scales that are hard to mimic by local noise. That is, the pulsar timing array is suited for reviewing physics with the common correlated timing signal, and the pulsar polarization array is suited for reviewing physics with the common correlated polarization signal. And then next question will be, well, for such a new tool, what kind of scientific case we can consider, we can explore, okay? In this study, I will demonstrate how to use the pulsar polarization array to detect ultralight axion-like wave dark matter. And we know dark matter is a puzzle of nearly 1 century. And since the first evidence was discovered in 1930s, it has been firmly established that dark matter exists in the universe with a significant share based on subsequent astrophysical and cosmological observations. And this was also introduced by Yang Bai in his talk. And because of the absence of the first principle for dark matter physics, the theory space for this topic, for dark matter, is huge. And the mass range spanned for the dark matter candidates on the market is over 80 orders of magnitude. And here, roughly speaking, these dark matter candidates can be classified into 3 categories. And the first one is macroscopic objects, such as primordial black holes. And the second ones are particle-like, and such as weakly interacting massive particles. And the third one is wave-like, or in short, wave dark matter. And wave dark matter is bosonic and has a mass much smaller than 30 electron volt. This means in a Milky Way-like environment, the occupation number for the Broglie volume will be much bigger than 1. Okay? Then this implies the formation of a coherent state with a strong wave nature within the galaxies. This is how wave-like dark matter gets named. And the axion-like particles are probably one of the most important wave dark matter candidates. And because of this complex formation, initial conditions, and their state is usually thought to be uncorrelated superposition of a vast number of particle waves. That is the profile for wave dark matter is stochastic. Okay, and even though in the last literatures somehow the profile for wave dark matter within our galaxy have been studied a lot. One common feature from these studies about wave dark matter is, well, its profile is oscillating. And here, the period is determined by the mass of the axions in this context in the temporal direction, and by its momentum in the spatial direction. And as for its amplitude, it is related to the local energy density of the dark matter halo. And one special class of wave dark matter is called fuzzy dark matter. For fuzzy dark matter, its mass is about 10 to minus 21 to 10 to minus 22 electron volt. And then in this case, the oscillation period for the dark matter is about 1 year. And the Broglie wavelength is of order 100 parsec. And this idea has been proposed by Wen Hu from University of Chicago about 20 years ago in order to address a series of small-scale problems. And one such example is core cusp problem. What is a core cusp problem? Well, the many-body simulations based on the standard WIMP scenario predicts dark matter halo within our galaxy. Okay, predicts dark matter halo with a cuspy structure near the galactic center. But based on the observations, astronomers told us that, well, this is not true. Actually, the profile of the dark matter halo near the galactic center is approximately uniform. And such inconsistency is called core cusp problem. And then in the framework of the fuzzy dark matter, because of the existence of the quantum uncertainty, a dense soliton-like core will form at the galactic center with its radius being about the de Broglie wavelength. In such a case, you can imagine the cuspy structure will disappear. Okay. And with these discussions, one interesting question will be, well, is dark matter the most powerful wave in the universe? Okay, And next, I will show the Pulsar Polarization Array could help to address this question. One interesting fact in relation to this is the axion-like wave dark matter can affect the pulsar polarization via an effect known as cosmological birefringence. And this idea was first pointed out by Shankara and George Field about 30 years ago. And this Shankara is exactly the one who has written this famous textbook on general relativity. And what is a cosmological birefringence? The idea is straightforward. We know the axion field can couple to the electromagnetic field via the Chern-Simons term. And because the axion field is parity odd, so in an axion field background, such a term will violate the parity, which results in a difference about the dispersion relations between the left and right circularly polarized light modes. And because of that, when the linear polarized light travels across the axion field, including the axion-like wave dark matter halo, its position angle will be rotated. And this effect is called cosmological birefringence. Well, this is reminiscent of the Faraday rotation, but actually there exists some important differences between cosmological birefringence and Faraday rotation. And firstly, the cosmological birefringence is determined by the difference of the axion field profiles between the two endpoints of the light path due to the topological nature of the Chern-Simons term. And as for Faraday rotation, we know its magnitude is proportional to the length of the light path, which is aligned with the magnetic field direction. Okay, this is the first difference. And secondly, cosmological birefringence, there is no frequency dependence. And as for Faraday rotation, well, we know, for example, for Faraday rotation, like the one in the interstellar media, somehow it will increase with wavelength square. Okay, this is the second difference. And thirdly, for cosmological birefringence, as said, it features oscillation with the period determined by the axion mass. Okay, in this context. But for Faraday rotation, there is no characteristic time dependence to be expected. And several years after Shankara and George Field point out this effect, Kamiokowski and his collaborators suggested to use CMB to detect the cosmological birefringence. And then in this case, the rotation of the position angle is determined by the difference of the axion field between at recombination and for the universe today. And after that, Xinmin Zhang and his collaborators from the IHAP in Beijing performed the first real data analysis, and this is, I think this is media report about their analysis. And nowadays, such measurement has become a standard task for the CMB missions. Okay. And more recently, with George Smoot and Yue Zhao, we have proposed to use linear polarized pulsar light to detect the cosmological birefringence. And then in such a case, the rotation of the position angle is determined by the difference of the axion field between near the pulsar at the photon emission around the Earth at the photon reception. Again, this is related to the topological nature of the Chern-Simons term. And particularly here, the axion field is a stochastic wave background. So its influence for the pulsar signals is common and correlated. So the pulsar polarization array is especially suited for its detection. Yes. And before I show you some project sensitivities, make a comparison about the cross correlation between the pulsar timing array detection of the stochastic gravitational wave background and the pulsar polarization array detection for the ultralight axion-like wave dark matter. Let's find out their similarity and difference. The first formula is timing residue caused by stochastic gravitational waves. And as is known to Earth, and this effect is determined by two terms. One is called Earth term, and another one is called pulsar term. And the second formula shows the position angle residue caused by stochastic axion-like wave dark matter. And similarly, it is also determined by two terms. One is Earth term, and another one is pulsar term. They look similar, but let's keep in mind the underlying physics is different. As said, for the case of the detection, for the second case, somehow this effect is related to the topological nature of the Chern-Simons term. And with these two formulae, then we can calculate the two-point correlation function for the timing residue and the position angle residue. Okay. And in the first case, the Earth term interplay has a quadrupolar structure. And this interplay predicts exactly the Hillian's dance curve known to Earth. But in this case, the interplay between the pulsar and the pulsar term is less important. What is the reason? The reason is because the gravitational wave is relativistic. So it's the Broglie wavelengths and its competent wavelengths are the same, both of which are about several parsecs. Okay. And for the spatial correlation, we know the Broglie wavelength is length scale to characterize this correlation effect. Okay. Then you can imagine in such a case, the Broglie wavelength is much shorter than the average separation for the pulsars which have been used to construct the pulsar timing arrays. Okay, so pulsar timing arrays in this case is quite incapable to probe the spatial correlation induced by the pulsar term interplay. Okay, but the story is different for the second case. And for the second case, the Earth term interplay has a monopolar structure. And this interplay only generates a temporal correlation pattern. Okay. So in terms of spatial correlation, the information is relatively few. However, the dark matter is non-relativistic. So the Broglie wavelength is about 3 orders longer than its Compton wavelength. So for nano-Hertz wave-like dark matter, it's the Broglie wavelength is about hundreds of pascal or even longer. So this is comparable to or even longer than the average separation of the pulsars used to construct the array. Okay? And because of that, the arrayed pulsars will be able to probe the spatial correlation induced by the nano-Hertz wave-like dark matter. Okay, so this is important difference. Yes. Well, so here for the construction of the pulsar polarization array, some of them are relatively close and some of them are relatively far. So as long as some of them have a separation comparable to hundreds of pascal, this is fine. Okay. So here there's no need for all of them to have a separation comparable to hundreds of pascal. Okay. Okay. Now I can show you some project limits. Okay. And then this map shows the project limits for the detection of ultralight axion-like wave dark matter. And this map is provided by this public website. Okay, and then from this map, you can find the position. You can find the position of the pulsar polarization array. And here, somehow, this website just take our sensitivity curve in our paper, but actually, our estimation is quite conservative. I will come to this point later. Okay. Okay, I'll show this. And then, okay, as commented in a recent review on axion cosmology, the ultimate reach of the PTA approach is to think about the pulsar polarization arrays, and in which the polarization information on different pulsars in the network is spatially and temporally correlated rather than considered separately as a measure of Faraday rotation. And here, I want to emphasize, different from some other proposals, the analysis of the pulsar polarization array actually is ready, is quite ready by using the current data and the forthcoming data. Okay, and at this moment, the first PPA analysis with real data are being carried out by several collaborations. And next, I will show some results obtained from the work in collaboration with PAX PTA. And here, these 3 first authors, Xiao Xue is a postdoc in DESY, and Shi Dai is a PPTA member, and now he is in Australia. And Hongnan Lu, he was my former PhD student and currently a postdoc in Spain. And from the author list, you can also say Andrew, and I think that he is he is over there. Okay. And this collaboration was started last summer, and with Jin Ren, we made this proposal to the PAX PTA, and finally it got approved. Okay, and this analysis is based on the polarization data of 22 millisecond pulsars from the third data release of the PPTA in 2023. And here is the frequency band that we are interested in. And for these pulsars, the maximum observation time span is about 18 years from 2004 to 2022. And because this analysis is quite new, so we developed an analysis framework, including the residue modeling by ourselves. And from this formula, we can see how we model the observed polarization angle residue. Okay, and here the first term represents contribution from the axion-like wave dark matter, and the second term the white noise, and the third term red noise, and the fourth one deterministic residue, and the last one it is from the ionosphere corrections. And with such a modeling, then we perform a Bayesian analysis just using the likelihood, which is shown here. And the last formula is covariant matrix element, which is contributed by the signal. And it is exactly this element that defines temporal and spatial correlation pattern for the signals. Okay. And before I show you the results, okay, let me demonstrate some mock response of the Pulsar Polarization Array to the signals. And for the in the left panel, okay, we inject some signals into the mocked noise data, okay, and then we can say in such a case, and the two peaks appears in the Bayes factor curves. Here we consider two Bayes factors. One is Bayes factor for the full correlation scenario, full correlation signal scenario against the null signal scenario. Okay, so we can say there is a clear red peak in this region. Okay, this is not strange. Okay, there is some signals, so this is not strange. Then we can say some peak in such a Bayes factor. And in addition to that, we also analyze the Bayes factor for the full correlation signal model against the autocorrelation only signal model. Okay. The reason is we want to make sure indeed the cross correlation plays a role in this analysis. Okay. Because for these scenarios, their difference is from with and without cross correlation. Okay. And indeed, in such a case, we can say in this black curve, there exists also a peak. Okay. So in this sense, we can say, well, the appearance of these double peaks in the Bayes factors, well, could serve as a smoking gun signature for this analysis. Okay. And as for the right panel, okay, we can see the different scenarios. Well, zero signal case, and the signal strength is 0.1 degree, signal strength is 0.3 degree, and we can say as the signal strength increases, the peak for the black Bayes factor then become sharper and sharper. Okay, this is consistent with our expectation. Okay. Okay, so this plot shows constraints that we have obtained from the individual pulsars. And in each panel, we demonstrate the curves from two pulsars just for clarity. Okay. And then we combine the contributions from these pulsars, and finally we get our master plot. And from this master plot, we can say for the exclusion limits, there exists a valley structure at the point about the inverse of the observation time span, okay? This can be understood. This is because if the mass is smaller than the inverse of the observation time span, then that means the oscillation period of the signal become longer than the observational time span. So the PPA will not be able to probe the whole profile, the whole oscillation profile of the signal. So certainly the sensitivity will get decreased, okay? This is how to understand the sensitivity in this side. And if the mass of the dark matter particle is larger than the inverse of the observation time span, then for that case, the axion field amplitude will decrease. Okay, this can be understood, okay? And because of that, somehow the sensitivities also get weakened as the value of MA increases, okay? But from the exclusion limits that we have obtained, we can say for certain mass region, especially the mass region for the fuzzy dark matter, actually our results represent the best limits so far for this scenario, okay, in constraining the Chern-Simons coupling, okay. And in addition to these features, from these curves, we can see some sharp peaks for relatively large axion mass, okay? And then a question is, well, whether these sharp peaks are caused by signals, okay? And the answer out, what we need to do is just to calculate the Bayes factors. And as discussed above, here we calculate the two Bayes factors for the full correlation signal model against the non-signal model, and a full correlation signal model against the autocorrelation only model. Okay. So for the first case, we can say indeed for corresponding to these sharp peaks, well, some other sharp peaks also appeared for the Bayes factor of the full correlation signal model against the now signal model. Okay. However, in the second calculation, there is no sharp peaks, and we can say, well, the black curve is quite flat in this region, okay? So this means that, well, these sharp peaks appearing in the exclusion limits are more likely to be caused to some unknown noises instead of the signal, okay? So this is a conclusion. And this discussion also highlights the value of the pulsar correlation in recognizing the nature of the data, okay? So overall, no peaks in the Bayes factors of the full against the auto to be have been discovered. This means that no axion-like wave dark matter signal signature have been observed from this set of data. Okay. From these discussions, we can immediately recognize some interesting directions for future explorations. And firstly, we can extend the PPA analysis from the Pulsar PPTA data to other active PTA programs, and also from the millisecond pulsar to normal pulsars. Okay. And actually here, I think this is very interesting, because in our original paper, or for our original motivation, is closely related to the pulsar timing array. Okay, and at that moment, well, we just want to make use of the polarization data from the PTA programs. But actually, sometime after that, our astronomer colleagues told us that probably it is better to use normal pulsars to construct a pulsar polarization array. And there is a couple of reasons. And the first reason is there are many more normal pulsars within our galaxy which have been stably monitored. This is the first reason. And second reason is compared to the millisecond pulsar, for some more normal pulsars, they are brighter, okay? They are brighter. And this is an important factor which may influence the precision of the polarization measurement. Okay, so here I think an interesting next step is to explore the constraints from the pulsar polarization array constructed from the normal pulsars. And in addition to that, we can apply the full correlation techniques of the pulsar polarization array to the pulsar timing array detection of axion-like wave dark matter. Actually, it has been known for a while that pulsar timing array can be applied to detect ultralight wave dark matter. And this idea was proposed by Rubakov and his collaborator about 10 years ago. But unfortunately, Rubakov passed away I think the year before last. Okay. The idea is like this. As said, for wave-like dark matter, its density profile actually is oscillation. So this will cause oscillation of the metric within our galaxy. Okay. And because of this effect, you can imagine some non-trivial timing residues for the arrayed pulsars will be generated, okay? And then based on this effect, the ultralight wave dark matter can be probed, okay? And then after this proposal, several PTA collaborations, including the PAX PTA collaboration, European PTA collaboration, and nano-Grav collaboration, all of them have delivered their first results to constrain the ultralight wave dark matter just based on the timing data. Okay. However, for all of these analyses, the cross correlation hasn't been taken into account. This means that actually some important message from data actually has been missed. Okay, so this could be another direction to explore, just by applying the full correlation techniques for the PPA to the PTA. Okay, and in addition to that, we may also consider correlating the PPA and the PTA to further strengthen their capability in recognizing the nature of the signals. And for the PTA detection, that is essentially gravitational, okay? But for PPA detection, that is non-gravitational. So in this sense, they may form a nice complementarity in detecting astrophysics or fundamental physics. And in addition to these interesting directions, we may also consider to extend the explorations from the radio band to a high frequency band. And about 2 years ago, the Fermi-Lett collaboration published the first constraints on the nano-Hertz gravitational wave background, just using a gamma-ray pulsar timing array based on their data collected in last decades, okay? And this is quite interesting in the sense that even though somehow the statistics is very limited, well, this can be understood because the Fermi-Lett is not a dedicated pulsar timing array mission, okay? So even though statistics is limited, but such a high frequency pulsar timing array can benefit from a suppression of intrinsic red noise of dispersion variance. And you don't need to know what it is. So here you only need to know this is one of the main noises for the detection of nano-Hertz gravitational wave background. Okay, this is the first thing you need. And second thing is this type of noise is inversely proportional to the square of the frequency. Okay, so if you go to the high frequency region, then this kind of noise tend to be suppressed. And then following this effort with my student, somehow we also apply the high frequency pulsar timing array for the analysis, for the detection of the ultralight wave dark matter. And this panel shows the constraints that we have obtained. And here the red curves represents the sensitivity that represent the exclusion limits that we have obtained using the gamma ray pulsar timing array. And here, these black curves, the solid one, dotted one, and the dashed one are obtained by PPTA, EPTA, and a nanograph, respectively. So if you compare the red curve and these black ones, you can say in the low mass region, actually their difference is not that big. But for the high mass region, the difference becomes larger. Well, the reason is because for the gamma ray PA, somehow the data is photon-based. Okay. And because the statistics is quite a few, so that means the time separation between the photon receptions actually tend to be long. And because of that, the gamma ray PTA loses its capability in detecting the ultralight wave dark matter. Okay. Okay, and then you can imagine we can also extend such effort from the pulsar timing array to the pulsar polarization array. So in the future, there exists possibility to construct a pulsar polarization array in the high frequency band. For example, using the IXPE or EXTP. Okay, so by making these efforts, somehow maybe we can build up a complete scheme for the PTA and PPA science. Okay, so here are take-home messages. To fully extend the physical reach of pulsars as a precision astronomical tool, we have developed the methodology of pulsar polarization array. And as one scientific case, we demonstrated that the PPA can be applied to detect the axion-like wave dark matter as a common correlated signal. And the first constraints with real data are expected to be released very soon. And the PPA and the PTA could be further correlated to further strengthen their capability in recognizing the nature of signals. And the joint PTA-PPA methodology could be also extended from the radio band to the high frequencies in the future. Okay, stay tuned. I will stop here. Thank you for your attention.
Questions?
So here, okay. We can find the message about your question from this plot. Okay, so here the SA is characteristic signal strength. Okay, so from this plot, we can say to what extent somehow the current data can constrain the rotation angle of induced by the signal. Okay, so you can see, for example, here, degree, yeah, degree, yes. Okay, so like, well, about 0.1 or slightly below that, yeah.
So may I ask one?
Yeah,
sure. So my understanding about the dark matter is it only interact through gravitational interaction. So I cannot directly say how it affects the polarization of the pulsar signals.
Uh,
Could you please explain this a little more?
Actually, this is not accurate. Okay, so there exists possibility that the dark matter interacts with the normal matter only by gravitation. Okay, there exists as a possibility. Okay, but this doesn't represent all possibilities. So actually, for more possibilities, actually the dark matter can interact with the normal matter in a non-gravitational way. Okay, so for example, in this case, oops. Here, A is a classical profile for the dark matter. Okay, so in this scenario, the dark matter interact with the electromagnetic field via a topological interacting term.
This is the transformer term.
Yeah, transformer term. Yes, yeah. Certainly, this is non-gravitational. Okay.
Then what's the reason that we cannot see this kind of phenomena in our laboratory experiments because the coupling is too small?
Okay, so here actually, I think people are making efforts in all directions. Okay, so here, what we are considering is just to utilize astronomical tools to detect ultralight axion-like wave dark matter. And certainly there exist lab methods to detect this kind of dark matter. Okay. Yes, this is also possible. So here the question is just because we don't know how strong the transimus coupling is. Okay. So this is, I think somehow in a general context, okay, this is just a free parameter. Okay. So we don't know whether this scenario is correct. And if this scenario is a right scenario for dark matter, we don't know what is the right value for the transimus coupling. Okay, so we need to do experiments or perform observations to find this out. Okay. Yeah. Oh. For this, let me see. For this mass region, I think it is difficult. Okay, for lab experiment. But several years ago, I think J.S. Taylor and maybe his student somehow they had some proposals. Maybe just for, I think just for same based on similar effects, cosmological birefringence. But I think somehow that is in a different mass region, I think. Probably for that case, I think it will oscillate faster. Okay. But in this case, I think the oscillation period is 1 year. But for lab experiment, actually, I think this is not necessary. Okay. Megahertz. I think if it oscillates in, I think for megahertz,
so that won't be ultralight dark matter candidate. The ultralight dark matter axion particle. So the mass cannot be in this kind of frequency range in our laboratories.
Okay, so the answer is like this. Okay, so for megahertz, I think it is difficult to use this, to probe. But yeah, we have a different method. We have the pre-Markov conversion process-based experiment. Okay, and for that case, we expect in an external magnetic field, somehow the axion particles, for example, created by the sun, okay, can be converted into the photon signals. Okay, so for that case, I think megahertz is certainly fine. Okay.
I think Professor Lippman is just providing a natural explanation for why this avoids, this just escapes the laboratory test, right? This kind of coupling by involving the ultralight axion-like particle. The frequencies not in the range about.
A dark photon, a very light dark photon, could also couple to FF twiddle through a dimension 6 term?
This is a good question. Its question is, okay, whether somehow we can apply this idea for the detection of dark photons. Because dark photons could be also a candidate for ultralight with dark matter. And then his question is, okay, for dark photon, maybe you can consider the FF tilde term, okay? And what I can imagine, okay, for example, like a 6-dimensional operator. It could be FF tilde and F prime. F prime is the field strength of dark photon. Okay, okay. So at this moment, I don't have a quick answer because I'm not very sure. Okay, such operator can be properly generated because of the Landau-Yang theorem, because constraint from Landau-Yang theorem. And yeah,
the standard Faraday rotation, dark photons, like yeah, you need a magnetic field, something like that, to really cause the whole rotation, right? So that's, I mean, if your filter by itself, the field derivative, that wouldn't do anything.
Yeah. So we just want yeah. Okay. This is our expectation. Okay. But as said, somehow, actually, this is something currently being explored by myself and my collaborator. Yeah, so yeah, because somehow, if this can be done, this means then it means that the applicability of the Pulsar polarization array can be broadened. So not just for the axion-like with dark matter, but also for dark photon with like dark matter. Right? Because for that operator is okay, it can be also parity violating. Okay, so.
So last chance. No questions. So let's thank our speaker again and.